I welcome you once again to another phase of explanation on Math 312, which is Real Analysis 3. From our previous explanation, I can still recall that I gave a very clear explanation to this example one, and I believe we got the main point that I actually explained from the previous video. Now, let's move straight to the next example, which is example 2. So, in this case, now we want to consider example 2. So let's take the next example, which is example 2. So for example 2, let's say we are actually given a function. We are given a particular function fn of x, a sequence of function of this nature. Let's say we have this as n squared x, then we have 1 minus x, then raised to the power of n. So given this kind of sequence of function, we are given this sequence function, then a range is actually given for x. Okay, x is bounded below by 0 and is bounded above by 1. Please take note. And at the same time, where our n starts from 1, the first term, second term, third term, and the likes. Okay, when you have a sequence, like let's say you have a sequence of 2, 4, 6, 8, 10, then like that. So this is when n is equals to 1. This is the first term, this is the second term. So n ranges from 1 to infinity in that case. Now, what do we want to do, or what do you want to prove? What do you want to try to prove in this question? It says given fn x equals to this, such that x is in this range, is bounded below by 0, and is bounded above by 1, then show that, so let's say we want to show, please take note of this proof. Okay, it's very, very important. Show that if you take the integral of the range of x given to you for all x, and then under the integral, they will now have limits as when n tends to infinity of the sequence function given to us with respect to x. That is, you are now having a limit function under the integral. So is this thing equivalent to the is it equivalent to when the limit is not under the integral? So the limit now is outside in this case. The limit is outside the integral in this case now, whereby your fnx of dx is the only expression that you have under the integral. So are they equal? That is when you take the limit inside, or when you take the, okay, if you take the limit to be under the integral and then the limit also outside the integral, if you end up solving this, if you evaluate this expression, are they going to be the same? It can never be the same. Okay. And then what if I now ask you, under what condition are they said to be the same? The condition is that it's actually when you notice that this fn of x, if it's if it is uniformly convergent, okay, if it's uniformly convergent to zero, or you say it converges, this thing can only be true. Please take note, this expression here can only be equals to each other if this sequence function converges uniformly to 0. I repeat, these two expression can only be correct, they can only be equals to each other under what condition? It's actually under when this fnx converges uniformly to 0. And then uniform convergence is what I'm going to explain after this example. We still have like two more examples to go. This example 2, I still have example 3, I still have example 4. In fact, I have up to 5. So I'll make sure I explain everything completely. That's why I'm trying to take this thing step by step. So please take note. Under what condition is this thing correct? It's actually when this from fn of x is uniformly convergent. So I did been have explained uniformly convergence now. I will just go and show it. And if that thing converges to 0, then I don't need to evaluate this thing separately. I'll just end up telling you that, okay, if I'm able to show that this thing converges uniformly to 0, I'll just end up telling you that this is correct. But now we have not moved into the topic which is called uniform convergence. We've not done that. Okay. So whatever you have to do now here is that they just want us to show that this is equals to this. But that is not the question. The question says show that this thing here is not equal to this. So me, if I try to tell you to show that this is not equal to this, so what would be my final conclusion? That means this fnx eh, does not converges uniformly to 0. That is the reason why it is not true under integral. Okay, so please take note of that. Now let's move straight to the main point of this question. So this is our main target. We want to show that this left hand side, is not equal to the right hand side. So that means I will take it one after the other. Let me consider this left hand side. So for the left hand side of the equation, which says that we have integral for all x, for all the range of x given to us, and the range of x is from 0 to 1. That is, as you can see, x is a member of, is bounded below by 0 and is bounded above by 1. So if you have something like this, you should know that you are dealing with integral such that this is bounded below by 0 and this is bounded above by what? By 1. So that's how it is. So let me still leave it as for all x. Then in the next line, I will write 0 goes to 1. So under the integral for the left hand side, I have the limits to, the limit is actually inside the integral. And then the fnx given to us, okay, this is our left hand side of the equation. Recall from our previous video, okay, if you go and check, I think part 2 or part 1 or so, I explained pointwise convergence, and I believe that from the explanation of pointwise convergence, I was able to tell you that there exists fnx, okay, sorry, let's say you have fn of x to be a sequence of a function. Then I set something such that there exists a real valued function f of x, right? At the end of the day, I end up telling you that that f of x is actually equal to, okay, it's actually equal to the limit as when n tends to infinity. That is, when you take the limit as when n tends to infinity of that sequence of function, then that will be equivalent to that real valued function that is being existed in that theorem, in that definition rather. So that means the whole of this expression here, okay, is actually equivalent to what? F of x dx. So sometimes you might end up seeing the proof. Then I say show that limit as when n tends to, sorry, they might not even write limit as when n. You might end up seeing this left hand side as, okay, show that for all x, f of x dx is equivalent to the limit outside of n tends to infinity of, for all x, then you now have fn x dx. So you must understand, understanding matters. So you should know that this f of x is equivalent to the limit of fn of x as when n tends to infinity. So I just want to try to call your attention to that. So remember that I've explained this in the previous definition from our previous video. So now looking at this now, I want to evaluate this left hand side again. I'm still on this left hand side. Okay. So the range for all x now, like I said I'm going to put the range now. 0 goes to 1. I've inserted the range. So the next thing for me to do from here now is to take the limit as when n tends to infinity of fnx. And fnx is given to us as n squared x, 1 minus x, then raised to the power of n. I think that's what I have as my fnx. So I believe I can actually solve this. Now go ahead with this. So this limit is inside, right? I have this limit. This limit is actually inside the stuff. Okay, no problem. So please take note of this explanation. Now that we have this expression here, I notice that I want to integrate this expression here with respect to it. But let's take the limit first. Let's take the limit of this. Okay, before I integrate, I will have to take the limit, right? Before I integrate, I will take the limit since the limit is actually inside the integral. So taking the limit of this, okay, the limit is actually based on n tends to infinity. So any other letter inside the integral will actually move outside. So this x can come outside from the integral, sorry, from the limit rather. This x will come outside from the limit, so the x is outside. So I'll be left with limit as when n tends to infinity. So I'll be left with this n squared, then open bracket 1 minus x raised to the power of n. This n cannot come outside since it's already inside the bracket and is being subtracted from 1. Okay, so I have all this expression here in a bracket, then dx. So I have to solve this inside. I have to solve this first. Okay, I have to take the limit of this. So to take the limit as when n tends to infinity of this expression here, you're not really familiar with taking limit of this kind of function, but it's not something that is really hard. Let me just tell you one thing. There is a concept that says that if you have any expression in a bracket and that bracket is being raised to the power of infinity and that expression is being raised to the power of infinity, or let me just say anything raised to the power of infinity, we always have it as 0. Because most essentially, what I used to come across with is just when I have e raised to the power of infinity, and that's 0 in that case. As when e tends to infinity, when you have e raised to the power of infinity, I think that should be equal to 0 also. So I believe that we can also apply it here. Any expression here that is being raised to the power of infinity, it must give us zero. So that's what I want to do in this case now. So in this case now, I have 0 goes to 1. Then I have x outside the limits. Okay. Okay, sorry. Let me clear that off. I have x, this is it here. So limit as when n tends to infinity of this expression simply implies that I have n squared. N tends to infinity. That means n is equals to infinity. No, if n tends to 2, I'll put 2 squared. So if n tends to infinity, I'll put infinity squared. So I have infinity squared here, open bracket, 1 minus x. Then this n is also infinity. So I notice that I'm seeing something in the bracket raised to the power of infinity. That means the whole of this expression here, so as far as it is being raised to infinity, the result will give us 0. And 0 times anything, okay? I have infinity squared, which is still infinity. Then infinity times 0, okay? That will automatically give us 0. 0 times anything is 0. So I can easily tell you that, I still have dx out here. So sorry for that. So I believe you can see that. So now I'm still on my left hand side, which says I have is integral from 0 goes to 1. So then I have x here. So inside this expression here, I have infinity squared times 0, and 0 times anything is already equals to 0. So I have dx here. So then this result should give us 0 goes to 1, x times 0, that's 0, then dx. So that's what I have left in that case. So if I integrate 0, okay, what would that give us? Okay, let's say this constant go outside. Now I'm left with just 0 goes to 1 dx. And then this is just saying that you have 0 times. This 0 times 0 goes to 1 dx. And I believe that if you integrate dx, that's x. Because there's an invisible 1 here. Hold on, I have to do something. Clear this off. 0 goes to 1 here. No, there's an invisible 1 here. Such that this invisible 1 can be expressed as x is power of 0. And when you integrate x is power of 0, that's x is power of 0 plus 1 over 0 plus 1. And that's x is power of 1 over 1. And that is x. So if I integrate this expression, I have x. Even though you insert the lower limit and the upper limit, 0 goes to 1, you still end up multiplying this result here by 0. So automatically speaking, I have 0 as my final answer. So 0 times anything here, that will give us 0. So in a nutshell, I noticed that the left hand side of my expression, after solving everything, the final answer is what? Is 0. Done. Now let's consider the right hand side. So if the right hand side gives us the same thing as 0, then what happens? That simply implies that the function given to us, this sequence function given to us, that means it converges uniformly to 0. Okay, that's just how it works. But if we solve the right hand side, and let's say we now have our right hand side to be equals to 2, that means they are not equal to each other. Since they are not equal to each other, that means that sequence function that is being given to us, it does not converge uniformly to 0. Then that's just what it means. So I'm just assuming that it is 2, not that it is 2. So let's solve it out. So we don't know yet. So let's try to find the right hand side of the equation. So let's consider the right hand side of the equation this time around. So okay. Just hold on. So let's consider the right hand side of the expression. For the right hand side, recall that our right hand side here, let me show it to you guys. This is the right hand side of the expression. This is it. Okay, this is it. Okay. Right hand side is actually when the limit is not inside the integral, when it's outside. Okay. So that's what I want to solve now. So the limit is actually outside the integral. I have range for all x and I have fnx dx here. So this is very, very straightforward. So now let me substitute all the values that we have that's available. The range for all x is still 0 goes to 1. It's bounded below by 0 and it's bounded above by 1. So in continuation, my fnx is what? Is given to us as n squared x 1 minus x raised to the power of n then times dx. So how will you integrate something like this? But before I start, I can actually look at this. I want to integrate this expression with respect to x. That means any other letter, we take it as a constant. Any other variable that you have in this expression, you take it as a constant. So that means n is not in terms of x. So n squared can actually go outside from this integral. but not outside the limit. Okay, since the limit is taking n tends to infinity. So let me write that down here. I still have my right hand side as limit as when n tends to infinity. I already said that this n squared will come outside from the integral. N squared will come outside from the integral. I have 0 goes to 1. Then I'll be left with just x times 1 minus x raised to the power of n, then dx. So when you get to this point, I'm only integrating this with respect to x. And I notice that any other letter is a constant. Okay. So this n here now is a constant. It's like saying I have 1 minus x all squared, or when n is 2 or something like that. Initially, we are actually given n as 1, 2, first term. So n is a constant. So trivially, it's a constant there. So which satisfy the condition given to us from the question. So I've taken off these two. So this n is just like a constant. So I have to use substitution method there. Using substitution method, that means I will look for what to substitute for this 1 minus x. So I can decide to call this. I can say let this represent any letter that you want. You can let it represent you any how you want it. So let me write it out clearly. Using substitution method, let u represent 1 minus x. Okay. If you let u represent this, that means what will be your x? From this, if I make my x as subject of, because I want to transform all this letter x back to another letter, and I want to use u in that case. So that means if u is equals to 1 minus x, then what will be your x? Because I have to express x in terms of u. So that means x minus s comes like this, u comes like this. Then I believe if you make x the subject of the formula here, my x will be equals to 1 minus u. So I already have this result. So I need to transform this dx also. And how will I do that? Du over dx. Differentiate this with respect to x. And I think that will be minus 1. Okay. So when you cross multiply, in that case, if I cross multiply here, I should have du equals to minus dx. Mind you, I want to make dx the subject. So use multiply both sides by minus 1. So I have minus du equals to dx. So my dx now has been substituted for what? Minus du in this case. So now that's not all. We still need to consider the range. Now for the range, when I'm referring to range, you know what I mean by that. This range is for x, okay? When x is 0. Now remember that x is a member of 0, 1. Okay? It's bounded below by 0 and 1. So when x is 0, this range here, dx, you are integrating this thing with respect to it. That means this range 0 goes to 1 is for x. And which implies that um we can actually relate it from here. So I have u to be equals to 1 minus x. So if x is equals to the lower limit for the range, which is 0, if x is equals to 0, what will be our u? Our u equals to 1 minus 0. That means u is 1. What if when x is equals to 1 for the upper limit? So what will be our u? 1 minus 1. So that's 0. So I think that's all we need for now. So now let's go ahead and substitute. The right hand side of that expression given to us now will be limit as when n tends to infinity of n squared, right? So for the range now, when x is 0, u is 1. And when x is 1, u is 0. So I've transformed the range in that case. X is already equals to 1 minus u. So I've substituted it for 1 minus u. And 1 minus x has been substituted for what? For u. The raised power of n. And I have dx. This is very easy to solve. So I can just go ahead and expand this bracket. So I can actually have my right hand side of the expression now to be equals to limit as when n tends to infinity of n squared, right? So in this case now, sorry, this dx now, there's something missing. Dx has not been, I've not substituted dx yet. Dx now is equals to minus du. So I'll just clear it off now. And I will insert dx now has been substituted for what? Negative du, according to what you have here. I think that's complete now. So there's a property of integral that says that if you have the integral of a goes to b, properties of integral from mathematical method, which is math 251. If you have the integral of a goes to b, it's equivalent to the negative of when you swap the range, b goes to a. Okay, that is if you have integral of, let's say, 0 goes to 2, this is equivalent to the negative of what? 2 go back to 0. I said, I think that's a property. So I want to clear off this minus. That's why I want to transform this so that the minus can come outside, then I will get rid of the negative sign. So nobody will tell you what to do in that case, but at least just use your IQ to deduce that. So this one goes to zero now. When I swap it, I will have negative of zero goes to one of what? 1 minus u in a bracket times u is to the power of n, then times minus du, such that if this minus multiply this minus, okay, then I will end up having plus. Minus times minus is plus. So therefore, I have my right hand side of the expression now to be equals to limit as when n tends to infinity. Minus times minus is plus. So I'm left with just n squared, right? Then integral of 0 goes to 1. So minus and minus is plus. So I think, please take note, it's multiplying. No, don't write n squared plus. No, it's multiplying. Is that clear? Times, okay. So minus will multiply this minus, that's plus. So it's not that you have to separate it. There's a dot here. Please take note. So 1 times u is power of n is u is to the power of n in that case, minus. Then u is to the power of 1 times u is to the power of n. According to the indices, that will be, according to indices now, that will be 1 plus n. You add the powers together. This is in a bracket. Please take note. They are multiplying. 1 times this is this, minus this times this is this. So you have it in a bracket. Then times du, since the negative sign is gone already. Okay. So I think this will be equivalent to limit as when n tends to infinity of n squared. So if I integrate u raised to the power of n with respect to u, that should be u raised to the power of, you add 1 to the power, just add 1 to it when you integrate it over, repeat the index back, minus, when I add 1 to this after integrating, if you integrate now, you add 1 to this, that will be 1 plus n plus 1. That will be u raised to the power of 1 plus n, then plus 1, okay? Then you have to repeat everything you have up there as your denominator too. So this is the integral. Mind you, I still have the range from 0 goes to 1. So you see, I'm trying my possible best to give an explanation to this one after the other, step by step. So I don't want to skip any steps. That's why I'm giving it to you line by line. So then I have limit as when n tends to infinity in this case, right? Such that now I have n squared. So here now I have u is power of n plus 1 all over n plus 1. So if I add this together now, 1 plus n plus 1, that's u n plus 2. And for this down part too, that's n plus 2. So mind you, who owns this range? Remember that is for you. Hey, the range here is for you. Remember, check it up here. It's for you. 0 goes to 1. So don't go and substitute this 0 goes to 1 for n. You are considering just you only. So if I consider that limit for you only, what will I have? I'll have n squared here. Sorry, I don't want to use that square bracket. So let's substitute for the upper limit when u is 1. When u is 1. So I'll have 1 raised to the power of n plus 1 over n plus 1, right? Then minus, when u is 1, I will have 1 raised to the power of n plus 2 over n plus 2. So this is for the upper limit. Please take note. Minus, now let's take the one for the lower limit. Lower limit, when lower limit is 0, I have 0 raised to the power of n plus 1 over n plus 1 minus this u now is already for the lower limit 0 raised to the power of n plus 2 over n plus 2. So I believe this is clear now. Well, this is for the upper limit when u is equals to 1, and this is for u equals to 0. Please take note. Take note of how I put it in the bracket. So that's how I'm trying to do it one after the other, please. That avoid any mistake, any slight mistake, then I'm very sure you're not able to get the correct answer in that case. So now that I have n squared here, so in this bracket now, 1 raised to the power of anything. This n serve as n equals to 1, 2, 3, first 10, second 10, share you graph. So if you take 1 raised to the power of 1 plus 1, that's still 1 squared, which is 1 times 1, that's 1. 1 times 1 raised to the power of anything, whether it's infinity or it's still 1. Okay? Aside from that one I said is 0. So in this case, 1 times 1 raised to the power of 1 times 1 times 1 times 1, 1 raised to the power of 22 million, 3 million, is still 1. 1 raised to the power of anything. Don't let me just use infinity. Okay, 1 is power of infinity, infinity itself is 1, so only in that case, only in the case of 1. But now this aside from this now, let's come back to what we are doing here. 1 is to the power of n plus 1, that is 1 over n plus 1. Then minus Same thing, 1 raised power of n plus 2 is still 1 over n plus 2. Then minus, you see 0 raised power of anything, that's 0. 0 divide this, that's 0. 0 divide this, that's 0. 0 minus 0 is still 0. Then I think everything here cancels as 0. So this is what I will have left. I will only be left with this guy here. I'll close the bracket. So what I have left now is just limit as when n tends to infinity of n squared. So if I find the LCM here, the LCM of this n plus 1 and n plus 2 is their product. Okay, is their product. So if this cancels this, I'll be left with n plus 2 times 1, that's n plus 2 in a bracket minus. If this n plus 2 cancel this one, I'll be left with n plus 1. N plus 1 times 1, that's still n plus 1. But please make sure you put this in a bracket to avoid any negativity error. Okay, so still on the right hand side, we now have it as limit as when n tends to infinity of n squared times, if I open up this bracket now, I should have n plus 2 minus n minus 1 over n plus 1 times n plus 2, which should now be equivalent to limit as when n tends to infinity of n squared times n cancel minus n, then 2 minus 1, that's 1. If I expand this bracket here, n plus 1 times n plus 2, I believe you should know that that will give us n squared plus 3n plus 2. You can try to do that on your own, that's all you have. So you get that result. So this right hand side is still equivalent to limit as when n tends to infinity of, I have n squared there multiplied by this, then that should be n squared over n squared plus 3n plus 2. And we all know that if you want to take the limit as when n tends to infinity of this kind of expression here, you have to consider the term with the highest degree. This term has an highest degree of 2, okay? So that means I'm dividing through by 1 over n squared. This is what I want to do now. Limit as when n tends to infinity. Divide each of these terms by n squared. That's, I believe you know how to do that now. So n squared, you divide this n squared by n squared. That is this one here, divided by n squared. This one here also, this n squared there, divided by n squared. So each of the term individually. This 3n also divided by n squared. And this 2 here divided by n squared. Everything one by one. And how did I come about this expression? It's from this concept that says that, okay, I have n squared over n squared plus 3n plus 2. That is this expression here. So what I did was just that I only multiplied up and down both the numerator and the denominator by what? By 1 over n squared and also 1 over n squared. That's what I did. So that if this cancel this, that means I've not done anything wrong to this expression. So if this multiply this, I have this result. If n squared multiply 1 over n squared, I have this. If this 3n multiply 1 over n squared, I have this. If 2n, okay, so that's the concept. It's understanding matters. It's not that I'm just using one kind of shortcut or anything. So that's how it works in that case. So if this cancel this now, my right hand side is still equals to 1 over, sorry, where is the limit? I should have put the limit first. I still have the limit as when n tends to infinity. If this cancel this, I have 1. If this cancel this, I have 1. If this cancel this, I have 3 over n. And if this cancel this, I have 2 over n squared. So as when n tends to infinity, which implies that I'll set n to be equals to, sorry, let me clear that off. Clear this off. So still on the right hand side, when I set n to be equals to infinity, that means I have 1 over. That means whenever I see n, I'll put infinity. 3 over infinity, 2 over infinity squared. We believe that any value that you divide by infinity, the result must give us 0. It's a must. Because we all believe that 1 over 0 is infinity, right? If 1 over 0 is anything divides 0, anything that divides 0, whether 2 over 0 is infinity. If 1 divides 0 and you have infinity, if I drop 1 across multiply, 1 times 1 is 1, 0 times infinity is 0 dot infinity. If I now divide both sides by infinity, this cancels this. So that means 1 over infinity is what? Is 0. If you also have 2 over infinity, that also gives. So anything that divides infinity, we always give you 0. So I'm left with 3 over infinity, anything like that's 0. This one, infinity square is infinity, 2 over infinity, that's 0. So that's 1 over 1 plus 0, that's 1. So I have it as 1. So therefore, you see, it's something that is really easy, but you must know how to solve this in a very fast way. So right hand side is equals to 1. So in summary, we believe that recall that our left hand side from equation star is 0. Now we now have our right hand side to be equals to 1, which implies that left hand side is not equals to what? Right hand side. And our left hand side is actually the integral of 0 goes to 1 when the limit is under the integral, okay, of fnx dx, which we are just proved that it is not equal to when the limit is outside the integral. And this is for the right hand side. I think this was what we wanted to prove now. So hence this actually ends the proof for example. I think this should be for example 3. Okay, example 2 rather. We still have more examples. Oh. We still have more examples. So we can actually just say that this limit cannot be taken under the integral sign. Okay. So however, if the sequence of function fn of x, which is equals to that n squared x, then that means okay, that means they can never be equal if the limit is under and if the limit is outside the integral sign. They can never be equal. Except they can only be equal. They can only be equal if it converges uniformly to 0. Okay? Let me just put it this way. Please take note of this. What I just said now is what I want to jot down now. So, however, this thing is not equal. Since it's not equal, then that means conclusion. What can you say about it? That means it does not converges uniformly to what? To 0. That's what it means. So what if it converges uniformly to 0? Then that's what I want right now. So that will just be, however, if that sequence of function given to us, that sequence of function, and what's that sequence of function? Let me write it out. If the sequence of function, I think we are given it as, it is given to us as n squared x 1 minus x is power of n. However, if the sequence of function fnx is equals to this, such that we are given x is a member of 0, 1, where n start from 1, 2 to infinity, okay. However, if this sequence of function converges, that is, if it converges uniformly to 0, then what happens? Then equality holds in, let's call this one equation star star. Okay, let's say that's equation star star. Then that means the equality holds in equation star star. That means they will always be equal to each other. So do you understand that? So otherwise, you know what that will be. So otherwise, that means it does not converge. So in other words, the reason for the result is that although the sequence of function converges to 0, but it does not converge uniformly to 0 in that case. Although this thing here, like that function converges, that function converges to 0. There's a difference between when fnx, this fnx here converges to 0. Hope you know. It converges to 0. How do I know that it converges to 0? Because I actually took the limit as when n tends to infinity of that fnx, this expression here. I took the limit, see it here, the limit, see the limit, and I tried this limit, and I have it as what? The limit end up giving me 0. The limit of all this guy here, I have it as 0. That means since I have this result as 0, the limit converges. That means since the limit is equal to 0, that means that fn of x, it converges to 0. Okay, but that does not really mean it converges uniformly to 0. It was, had it been this particular fnx, I didn't have explained uniformly convergence, and then you use the definition of what I've explained, maybe in that will be our next two videos. Okay, and let's say you try fn of x and then it converges uniformly to 0. That means I don't need to go through all this stress. Okay, I'll just end up telling you that that equality holds for the left hand side and the right hand side. But for this question, oh, please take note. This fns converges to zero. Why? Because when we actually took the limit as when n tends to infinity of fnx, the result converges to zero, which simply implies that it converges to zero. So the difference is that this only converges to zero, but we have not explained what convergence, when something converges uniformly. So it does not necessarily, it's not necessarily like it converges uniformly to zero. So we have to do that one separately and then confirm what that is going to give us. So I think this is just example two. So you can try this on your own. I have another example that you can try here on your own. You can try this. Let's say our fnx, you can try this on your own. Fns is equals to nx e raised power of minus nx squared. With this, do you know that this equation there is in your assignment, the previous assignment that you guys just submitted? So show that, let's confirm or prove or disprove that the equality holds or not. The equality holds for that left hand side and the right hand side. Are they equal or they are not equal? Remember what the left hand side is and what the right hand side is. So that is what you have to do. So try this on your own. Or probably I can decide to solve it now also. I can decide to solve this out myself. Okay, I can solve it. I can actually, I think it would be better if I just write it and solve it. But I wish you can actually try this on your own. Okay, then get back to me. You can send in your replies, maybe my comments. If you don't understand, comment, just drop a comment on my YouTube channel. So I'll make sure I reach out to you. Okay, so that is how it works. So just follow the same process in solving this, and then I believe you should be able to break it down. And you notice that if the left hand side is equals to zero, and then let's say the right hand side is equals to two, that means the equality does not hold. Okay, and what happens? Which means it does not converges uniformly. But if the equality holds, that means it converges uniformly to zero. So that's how it works. So this is for example, okay, let's just say this for example three. You know what? I'll solve, let me just make it more easier. I'll solve this question in my next video. Then after that, I'll move to example three. So we call this one, let's call this one example three. So I have example four, and I also have example five. So I have to solve the three of them completely before we move to the next topic, which is the uniform convergence. I'll still have to explain uniform convergence. Okay. For uniform convergence, that's where the Weierstrass theorem comes in. I'll make sure I explain it clearly. So, thanks for watching.